Heat does indeed increase the resistance of copper wire. As the temperature of a copper wire rises, its resistance also goes up. This occurs because the increased thermal energy causes the copper atoms to vibrate more vigorously. These vibrations impede the flow of electrons through the wire, effectively increasing its resistance. Derating wire at 125% for continuous use is a standard practice. Derating means reducing the maximum current a wire can safely carry. This is done to prevent the wire from overheating, which can damage the insulation and potentially cause a fire. The National Electrical Code (NEC) mandates this derating for continuous use applications. For example, a wire rated for 20 amps should only be used to carry 16 amps continuously after applying the 125% derating factor. If resistance increases, amperage decreases, assuming a constant voltage. This relationship is described by Ohm's law, which states that current is directly proportional to voltage and inversely proportional to resistance. Mathematically, this is expressed as current equals voltage divided by resistance. Therefore, if resistance goes up and voltage remains the same, the current or amperage will decrease. In this scenario, with the resistive heaters, the initial undersized aluminum wire likely experienced significant heat buildup due to excessive current. This heat increased the wire's resistance, but the increased resistance didn't cause the amperage to decrease initially in a way that protected the wiring. Instead, the higher resistance led to voltage drop along the wire, meaning less voltage was available at the heater itself. Because the heater's power output is related to both voltage and current, and the wire was already strained to the limit, the situation was unstable and led to further heating until the proper wire size was installed. With the proper wire, the resistance was lower, reducing the voltage drop, providing the intended voltage to the heater, and keeping the current within the design parameters. Over time, sustained heat can degrade wire insulation. This degradation can compromise the insulation's ability to prevent electrical shorts, creating a potential safety hazard. This is a primary reason for derating wires in continuous use applications. The NEC provides tables, such as those found in Article 310.15 and related sections, that specify the allowable ampacities of different wire gauges based on their insulation type and ambient temperature. These tables also provide adjustment factors for situations where multiple current-carrying conductors are bundled together, or where the ambient temperature exceeds a certain level. These adjustment factors are essential for ensuring that wires are not overloaded and that their insulation does not overheat. Consider a scenario where you have 3 current-carrying conductors in a conduit, and the ambient temperature is higher than the temperature listed in the ampacity table. In this case, you would need to apply both the adjustment factors for the number of conductors and the ambient temperature. For example, if the base ampacity of the wire is 30 amps, and the adjustment factor for 3 conductors is 0.80, and the adjustment factor for the ambient temperature is 0.91, the adjusted ampacity would be 30 amps times 0.80 times 0.91, which equals 21.84 amps. This means that the wire should not be used to carry more than 21.84 amps in this particular situation. The ampacity of a conductor is also affected by the type of insulation used. Different types of insulation have different temperature ratings, which indicate the maximum temperature that the insulation can withstand without degrading. Common insulation types include THHN, THWN, THW, and XHHW. THHN insulation, for example, is rated for 90 degrees Celsius in dry locations, while THWN insulation is rated for 75 degrees Celsius in wet locations. The NEC specifies the allowable ampacities for each insulation type in its ampacity tables. When selecting a conductor for a particular application, it is important to choose a conductor with an ampacity that is sufficient to carry the expected load current, taking into account any applicable derating factors. It is also important to choose a conductor with an insulation type that is suitable for the environment in which it will be used. For example, if the conductor will be exposed to moisture, it is important to choose a conductor with THWN or a similar moisture-resistant insulation. In addition to derating for continuous use and adjusting for ambient temperature and the number of conductors, it is also important to consider the voltage drop in a circuit. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. To calculate the voltage drop in a circuit, you can use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current constant, which is 12.9 ohms for copper and 21.2 ohms for aluminum. I is the current in amps, D is the one-way distance in feet, and Cm is the circular mils of the conductor. Circular mils is a unit of measurement used to express the cross-sectional area of a conductor. The larger the circular mils, the lower the resistance of the conductor. The NEC provides tables that list the circular mils for different wire gauges. To minimize voltage drop, it is important to use conductors that are large enough for the expected load current and to keep the length of the circuit as short as possible. It is also important to use conductors with low resistance, such as copper conductors. When installing electrical wiring, it is important to follow all applicable codes and regulations, including the NEC. The NEC provides detailed requirements for the installation of electrical wiring, including requirements for conductor sizing, overcurrent protection, grounding, and bonding. It is important to consult the NEC and to follow its requirements carefully to ensure that electrical wiring is installed safely and correctly. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical wiring from overloads and short circuits. These devices are designed to trip or blow when the current in a circuit exceeds a certain level, interrupting the flow of electricity and preventing damage to the wiring. The NEC specifies the maximum allowable overcurrent protection for different wire gauges. It is important to choose overcurrent protection devices that are properly sized for the wiring that they are protecting. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protection devices to trip and clear the faults. Bonding connects all metal parts of an electrical system together, ensuring that they are at the same electrical potential. This helps to prevent electrical shock hazards. The NEC provides detailed requirements for grounding and bonding. It is important to follow these requirements carefully to ensure that electrical systems are properly grounded and bonded. Electrical safety is paramount when working with electrical wiring. It is important to take precautions to protect yourself from electrical shock hazards. Always de-energize circuits before working on them. Use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. If you are not comfortable working with electrical wiring, it is best to hire a qualified electrician to do the work. The original observation about the resistive heaters drawing more current than expected with undersized wiring is a common scenario. The heat generated by the undersized wiring increased its resistance, leading to a voltage drop at the heater. While the heater itself might initially draw slightly more current due to the lower voltage, the primary issue was the excessive heat in the wiring, which could eventually lead to insulation failure and a fire hazard. Installing the correct wire size reduced the resistance, minimized the voltage drop, and allowed the heater to operate at its designed voltage and current, resolving the overheating issue. The heat buildup does degrade the insulation over time. This degradation reduces the insulation's ability to prevent shorts and ground faults. This is a key reason why proper wire sizing and derating are so important. Now let's consider different scenarios related to conductor ampacity and derating. Scenario 1: a 20 amp circuit breaker is protecting a circuit wired with 12 American wire gauge (AUG) copper conductors with THHN insulation. The circuit feeds several receptacles in the general use area. The conductors are installed in a conduit with 4 other current-carrying conductors. To determine if the wiring is properly sized, we need to consider the ampacity of the 12 AWG THHN conductor and the derating factors for the number of conductors in the conduit. According to NEC Table 310.15, B16, a 12 AWG THHN copper conductor has an ampacity of 30 amps at 30 degrees Celsius, 86 degrees Fahrenheit. However, since there are 4 current carrying conductors in the conduit, we need to apply a derating factor. NEC Table 310.15. C1 provides derating factors for the number of current carrying conductors in a raceway or cable. For 4 to 6 current carrying conductors, the derating factor is 80%. Therefore, the adjusted ampacity of the 12 AWG conductor is 30 amps times 0.80, which equals 24 amps. Since the adjusted ampacity of 24 amps is greater than the 20 amp circuit breaker, the wiring is properly sized for this application. However, it is important to note that the load on the circuit should not exceed 80% of the circuit breaker rating for continuous loads. Continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. In this case, the continuous load should not exceed 20 amps times 0.80, which equals 16 amps. Scenario 2, a 100 amp subpanel is fed by 3 AWG copper conductors with XHHW insulation. The conductors are installed in free air. The ambient temperature is consistently around 40 degrees Celsius, 104 degrees Fahrenheit. We need to verify if the conductors are appropriately sized for this installation, taking into account the higher ambient temperature. According to NEC Table 310.15, B16, a 3 AWG copper conductor with XHHW insulation has an ampacity of 85 amps at 30 degrees Celsius, 86 degrees Fahrenheit. Since the ambient temperature is 40 degrees Celsius, 104 degrees Fahrenheit, we need to apply a temperature correction factor. NEC Table 310.15. B2. It provides temperature correction factors for different insulation types and ambient temperatures. For XHHW insulation, the correction factor for an ambient temperature of 40 degrees Celsius is 0.91. Therefore, the adjusted ampacity of the 3 AWG conductor is 85 amps times 0.91, which equals 77.35 amps. In this case, the adjusted ampacity of 77.35 amps is less than the 100 amp subpanel. This means the 3 AWG conductors are undersized for this application, and larger conductors would be required to safely carry the load. Scenario 3, a motor nameplate indicates that it draws 40 amps at 480 volts. The motor is supplied by 8 AWG copper conductors with THHN insulation installed in a conduit with no other conductors. The circuit breaker protecting the motor is rated at 50 amps. We need to determine if the wiring and overcurrent protection are suitable for this motor application. According to NEC Table 430.22, A. The conductors supplying a single motor must have an ampacity of not less than 125% of the motor's full load current rating. In this case, the motor's full load current is 40 amps, so the conductors must have an ampacity of at least 40 amps times 1.25, which equals 50 amps. According to NEC Table 310.15, B16, an 8 AWG copper conductor with THHN insulation has an ampacity of 55 amps at 30 degrees Celsius, 86 degrees Fahrenheit. Since the required ampacity is 50 amps, and the 8 AWG conductor has an ampacity of 55 amps, the wiring is adequately sized. Now, we need to check the overcurrent protection. According to NEC Section 430.52, the overcurrent protection for a motor circuit must not exceed certain percentages of the motor's full load current, depending on the type of motor and the type of overcurrent device. Assuming this is a standard motor and a non-time delay fuse is used, the maximum overcurrent protection is 300% of the motor's full load current. In this case, 300% of 40 amps is 120 amps. However, if an inverse time circuit breaker is used, the maximum overcurrent protection is typically 250% of the motor's full load current, which would be 100 amps. The actual allowable value depends on the specific motor and breaker characteristics, so consulting NEC Table 430.52 and the motor and breaker documentation is crucial. Given the 50 amp circuit breaker, it appears to be appropriately sized, assuming it meets the NEC requirements for motor overcurrent protection. However, a careful review of the specific motor and overcurrent device characteristics is necessary to confirm compliance with the NEC. These scenarios highlight the importance of considering various factors when sizing conductors and selecting overcurrent protection. These factors include the ampacity of the conductors, the derating factors for the number of conductors and ambient temperature, the voltage drop in the circuit, and the requirements of the NEC. It is also important to consider the type of load that the circuit will be serving, as different types of loads have different requirements for conductor sizing and overcurrent protection. By carefully considering all of these factors, you can ensure that electrical wiring is installed safely and correctly. Let's delve deeper into the practical implications of heat generation in conductors and its impact on electrical systems. The resistance of a conductor is not a fixed value, it changes with temperature. This relationship is generally linear for most common conductors over typical operating temperature ranges. The temperature coefficient of resistance quantifies how much the resistance changes per degree Celsius or Fahrenheit. For copper, this coefficient is approximately 0.393 per degree Celsius. This means that for every degree Celsius increase in temperature, the resistance of a copper conductor increases by 0.393%. While this may seem like a small change, it can become significant at higher temperatures or in long conductors. Consider a 100-foot length of 12 AWG copper wire with a resistance of approximately 0.159 ohms at 20 degrees Celsius, 68 degrees Fahrenheit. If the temperature of the wire increases to 75 degrees Celsius, 167 degrees Fahrenheit due to high current flow, the resistance will increase by approximately 0.159 ohms times 0.393 per degree Celsius times 55 degrees Celsius, which equals approximately 0.34 ohms. The new resistance would be 0.159 ohms plus 0.34 ohms, equaling 0.193 ohms. This increased resistance will result in a greater voltage drop along the wire and reduced voltage at the load. The power dissipated as heat in a conductor is proportional to the square of the current and the resistance according to Joule's law. Power equals I squared times R. This means that even a small increase in resistance can lead to a significant increase in heat generation, especially at high currents. The heat generated in a conductor must be dissipated to prevent the conductor from overheating. The rate at which heat is dissipated depends on several factors, including the size and shape of the conductor, the insulation material, the ambient temperature, and the presence of airflow or other cooling mechanisms. If the rate of heat generation exceeds the rate of heat dissipation, the temperature of the conductor will rise, leading to further increases in resistance and heat generation, potentially creating a thermal runaway situation. Wire insulation plays a critical role in the safe operation of electrical systems. Insulation materials are designed to withstand high voltages and temperatures without breaking down. However, prolonged exposure to high temperatures can degrade the insulation, reducing its dielectric strength and increasing the risk of electrical shorts and ground faults. The temperature rating of an insulation material is the maximum temperature that it can withstand for an extended period without significant degradation. Common insulation materials include THHN, THWN, THW, and XHHW, each with different temperature ratings. It is essential to select the appropriate insulation type for the application, taking into account the expected operating temperature and environmental conditions. The National Electrical Code, NEC, provides detailed guidelines for selecting and installing electrical wiring, including requirements for conductor sizing, overcurrent protection, and insulation type. The NEC also provides tables that list the allowable ampacities of different wire gauges based on their insulation type and ambient temperature. These tables are essential for ensuring that wires are not overloaded and that their insulation does not overheat. In addition to the NEC, other standards and regulations may apply to electrical installations depending on the location and type of facility. These standards may include those from organizations such as the Institute of Electrical and Electronics Engineers, i.e., the National Fire Protection Association, NFPA, and Underwriters Laboratories, all. It is important to be familiar with all applicable codes and regulations to ensure that electrical installations are safe and compliant. Regular inspections and maintenance are essential for ensuring the continued safe operation of electrical systems. Inspections should be performed by qualified electricians who are trained to identify potential hazards and defects. Maintenance activities should include cleaning and tightening connections, inspecting insulation for damage, and testing overcurrent protection devices. By performing regular inspections and maintenance, it is possible to identify and correct problems before they lead to more serious issues, such as electrical fires or equipment failures. Understanding the principles of conductor resistance, heat generation, and insulation properties is essential for anyone working with electrical systems. By applying these principles and following the guidelines of the NEC and other applicable standards, it is possible to design and install electrical systems that are safe, reliable, and efficient. Furthermore, it's important to remember that practical experience and continuous learning are key to mastering the complexities of electrical work. Always consult with experienced professionals and stay up to date on the latest codes, standards, and technologies.